It's a story of vindication. In 1982, Dan Schechtman, the Philip Tobias Professor of Materials Science at the Technion Israel Institute of Technology, claimed he had discovered a new form of crystalline structure, one that conventional wisdom held to be impossible. For years, Professor Schechtman was ridiculed by his peers and even asked to leave his research group for continuing to insist that there was only one explanation for the image he had seen in his microscope. But by 2011, the discovery was so firmly established that Professor Schechtman was awarded the Nobel Prize in Chemistry. The day before receiving the award on December 10th, he visited the Department of Material Science at KTH to talk about the quasi-periodic crystal structure that came to be called quasicrystal. His lecture, presented here in full, is largely about his science, but it's just as much a tale of personal triumph.
Ladies and gentlemen, I welcome you to KTH and the Material Science Department. It's a very big day for us here today. We have a visitor from Professor Daniel Schechtman. And as you all know, he is the Nobel Prize in Chemistry 2011 winner. And during this time when he got the Nobel Prize, he was affiliated with the Israel Institute of Technology in Haifa in Israel. And the motivation, as everyone knows by now, for the discovery of quasicrystals. I also want to mention that we will have also some talks from Sandvik Materials Technology later on. But I think we will start this very special afternoon with Professor Schechtman's presentation.
Thank you very much for inviting me here. It's a great pleasure to see all these young, enthusiastic people and a good part of my family also. And I intend to give you a long talk because in the Nobel talk they cut me very short. So today I'm taking my revenge. So I will be talking about discovery of quasi-periodic materials. My name is Daniel Schechtman. I'm from the Technion. I also have a position at Iowa State University in the United States. Let's start with in the mid-80s. In the mid-80s, we had three surprising discoveries on the structure of matter and its properties. And they came year after year. And by now, all three of them got the Nobel Prize, year after year. 84, and then 85 and 96. 84 was the discovery of quasi-periodic crystal. And the discovery was actually made in 1982, but the paper was published in 1984. And the names on the paper are my name, Daniel Schechtman, Ilan Blech, Denis Gratias, and John Kahn. And later on, I'll tell you what each of them contributed to the paper. And then 1985 came the discovery of fullerenes. And now we have nanotubes and nanowires and all kinds of things. But nanotubes were a result of fullerenes. They were also called Bucky tubes, for those of you who remember, named after Buckminster Fuller, who had those geodons and so on. And then the third was high temperature superconductivity, 1986. Let me say a few words about this. Let's start from the end. High temperature superconductivity was a great surprise because people did not believe that you could have high temperature superconductivity beyond 30 degrees Kelvin. And so when Joe Bednorz and Alex Muller discovered high temperature superconductivity, it was a great surprise. But superconductivity was discovered at the turn of the century, long before that. So superconductivity was not a surprise, but high temperature superconductivity was. Fullerenes, there was no objection to fullerenes. This is another way that carbon atoms can be arranged. We knew, and last year there was a Nobel about it, that graphite can be, there are single layers of carbon and they can be separated, and those layers have very strong bonding within the layer, but very weak bonding among the layers, so that they can slide. And so here we have a layer which makes a ball, or a layer that makes a tube. So it was very nice to discover it, but there was no objection and there was no fight about it. Quasi-periodic crystals were a different story because it went against the grains of traditional crystallography, against the rule of traditional crystallography, and let me remind you that crystallography was, in the 80s, a mature science. That means the science that was established in 1912 had 70 years of experience, and the rules were clear, and there was nothing new to be discovered as people believed. Indeed, you could have discovered a new crystal, and you would identify the structure, and let's say that the structure was B2, so you had a big drawer of B2 structures. You put your new crystal there, you close the drawer and say, I'm happy. This was not the case with quasi-periodic crystals, and in my talk, this is what I will be talking about. But before we start, and I'm talking to the students, not to the experts, let's talk about order, about periodicity, and about rotational symmetry, because all of them are important in order to understand what is new about quasi-periodic material. So here we have a structure. Let's say it's a single layer of a cubic structure. And if I bring in this line, then you can see that the atoms are not only ordered, but also periodicity. So if I will ask you what comes next, you will be able to tell me, oh, I can tell you the exact position of the next atom and the next after, and so on and so forth. This is periodicity. Clearly, the order is seen. And now this periodicity can be found in each and every direction. Anytime you connect two atoms, you connect an infinite number of atoms, and there is periodicity along that line. And here is one more example. And you can do anything you want in each and every direction. Now let's talk about rotational symmetry. This crystal can be rotated. Oops, rotated. Now, let's add, you see, when it was rotating and came back to its position, you cannot really tell whether I did one full circle or maybe one full circle and 1/4. Can anybody tell? No, you cannot tell. So in order to tell, let me add a little handle. And so now let's rotate it with the handle on. Oops, 90 degrees, 90 more, 90 more. And so, as you can clearly see, we have a 4-fold rotational symmetry with this crystal. You can tilt it 90 degrees, and you cannot tell the difference, 90 more, and then it comes back to where it was before. So this crystal has, in this position, in this orientation, has a 4-fold rotational symmetry. So let's define the rotational symmetry. An image has a rotational symmetry if there is a center point around which the object is turned a certain number of degrees, and the object still looks the same. That is, it matches itself a number of times while it is being rotated. Well, I hope this is clear. And here are some examples. On the left, you see this card. It has a 2-fold rotational symmetry. You can imagine that you rotate it 180 degrees, and it looks just about the same. 3-fold, 5-fold, 6-fold. These are rotational symmetries. Now let's say a few words about crystallography, because we are dealing with the science of crystallography. Modern crystallography started in 1912 with the seminal work of von Laue, who performed the first X-ray diffraction experiment. This was really an amazing experiment, because von Laue proved in one experiment that X-rays have wavy nature and that crystals are indeed ordered as people thought before. Not only was his crystal ordered, it was also periodic. And the crystal that were studied from his first experiment for 70 years, hundreds of thousands of them were all ordered to fit the definition of a crystal and periodic. and there was no exception. Hundreds of thousands for 70 years. And bear in mind, the science of crystallography was a very strong precision science, and many scientists around the world worked in crystallography. It was not just a side little science. It was the basis of our understanding of the structure of matter. Very important and very stagnant too. So then there was a definition that emerged from our observations. A crystal may be defined as a solid composed of atoms arranged in a pattern periodic in 3 dimensions. This is from the book of Quality. I don't know if they still teach it, but it was a very good book. Still is. So here is the definition. Solid composed of atoms arranged in a pattern periodic in 3 dimensions. Simple. It says a crystal is. Another definition, which is exactly the same in different words. Atoms in a crystal are arranged in a pattern that repeats itself in 3 dimensions throughout the interior of the crystal. Same definition. And then something happened. By the way, before something happened, this is the book that we all studied, the book by Charles Kittel, and you cannot read the little words there, so I enlarge it for you. And look at the part that is marked. And what it says is the following. We can make a crystal from molecules which individually have 5-fold rotation axis, but we should not expect the lattice to have a 5-fold rotation axis. So, yes, 5-fold motifs, but no overall 5-fold symmetry in a crystal. So this was the wisdom. Now, let's look at the real space, at atoms in a material. So these are atoms in a diamond, in a crystal of a diamond. And there are no defects in this part of the crystal. This is a picture that I took many years ago. And the order of carbon atoms in diamond is periodic, and the allowed rotational symmetries here in a periodic structure are 1, 2, 3, 4, and 6. No 5-fold, and nothing beyond 6 is allowed in periodic crystals. Okay, no problem at all. Everybody agrees. Let's look at the reciprocal space, at the diffraction space of a periodic crystal. Here is a diffraction pattern. This is an electron diffraction pattern that is taken from a periodic crystal. And what you can see here is that these are not atoms. These are diffraction peaks in the reciprocal space. But the rules are very much similar. There is periodicity of the diffraction peaks in the reciprocal space, periodicity. Rotational symmetry is allowed are 1, 2, 3, 4, and 6-fold. No 5-fold rotation symmetry, and nothing beyond 6-fold, much like in the real space. And then something happened, and a new definition of a crystal have emerged. Let's see. This happened in 1992. By crystal we mean, this is the new definition, by crystal we mean any solid having an essentially discrete diffraction diagram. And by aperiodic crystal, we mean any crystal in which 3-dimensional lattice periodicity can be considered to be absent. It doesn't say crystal is. It says by crystal we mean very soft, very humble. It doesn't say a crystal have a discrete diffraction diagram. It says solid having an essentially discrete diffraction diagram. And by aperiodic, we mean any crystal in which 3-dimensional lattice periodicity can be considered to be absent. Very, very complex, humble definition. What it means is, hey guys, we are open to new discoveries in the field. This is a wonderful definition, a humble definition. Humble scientist is a good scientist. And this is a definition that was made by the International Union of Crystallography in the year 1991. And this is the definition they have arrived at, which is a major victory for the International Union of Crystallography to be so humble. It was not easy for them. Now, 1982 was the 70th birthday of crystallography. As I mentioned, in 1912, von Laue performed his first experiment, X-ray diffraction experiment. And by doing so, he created a science. Not only the name of the science was not crystallography. The name of the science was X-ray crystallography. To differentiate those modern scientists from the geologists who studied crystal by the shapes of the facets of the crystal that they have found in nature or grew in the laboratory. They said, we have a tool now, a precision tool. X-ray diffraction is a very precise tool. And we are not like these guys with the facets. No, no. We are X-ray crystallographers. And so it was the 70th birthday of crystallography. And this was the year the quasi-periodic crystals were discovered. Let me talk a little bit about 1912, because 1912 was a very interesting year to many of us, although this is a major event that happened at that time, but also you may know that the Titanic sank that year, and the Olympics in Stockholm were held this year, and also my institution, the Technion, the cornerstone was laid that year, and also Emperor Meiji of Japan, who opened Japan to the West, died that year. And I have a longer list, but I will stop here. So it was a very interesting year. By the way, the doyen of my department also was born that year. He died a few years ago. So now, what happened that we have a new definition for a crystal? And a definition of the crystal is the baseline of the whole science. This is the baseline. This is the definition of a science. So what happened? Well, let's look at my logbook. From April 8, 1982, as you can see on the upper right corner, this is a TEM logbook, Transmission Electron Microscopy logbook. And the alloy that I was working on was aluminum 25 weight % manganese. It was rapidly solidified. It doesn't say here. And it was one of a large series of alloys that I have prepared when I was on sabbatical at the National Bureau of Standards in Maryland. And academically, I was associated with Johns Hopkins University as a guest at the time. This logbook was not meant to be seen by anybody but me. I didn't write down all the little strange signs for the public, but you know, as history goes, now everybody saw this logbook, especially this page. So this is one of many pages, as you can see. And let us look at the experiments that I have performed that day. So on the right-hand side, you see plate number 1720, SAD, meaning selected area diffraction. And then we talk about electron diffraction. Number 2 is also selected area diffraction. The plate 1722, 28, and then 17, and then something starts. And you see this string of dots connected by lines. That means to me that this is the same crystal. I didn't move to another crystal. Everything was taken on the same crystal. Okay, these are little marks that I mark for myself. And then I saw a picture number 1724. I will show it to you shortly, this picture. And in that picture, as you will soon see, there were a few grains which were pitch black. Pitch black means usually in a good specimen that in a bright field image, that means that the transmitted beam is used to take the picture. It means that the transmitted beam doesn't go through that part of the crystal, rather the crystal diffracts heavily that the beam. Okay, and there's an aperture there, and you allow only one beam, and all the diffracted beam are stopped. You don't see them. And I said, wow, such pitch black crystals. I don't think I've ever seen such pitch black crystals. Let's look at the diffraction pattern. And the plate 1725 is SAD, selected diffraction pattern. 10-fold. had a 10-fold rotation symmetry, and I will show it to you shortly. And then let's go on here. I started to perform a series of experiments right away in order to find out what it was. And what I thought it was is a series of 5-fold twins, which I have seen in the past, before that year. So I knew about 5-fold twins. It happens in many materials, and I will show you a couple of examples here. And I said, okay, let me just find the twins and forget about it. So I performed a series of dark field experiments in the TM and could not find the twins. They were not there. So I said, well, maybe the resolution of the microscope is not so good, although it was a Philips 400, a superb microscope. Let me take a microdiffraction. So if you look down at place 1737 and the following two places, it says microdiffraction. Mu diff is microdiffraction. That means, for the non-microscopists among you, the two who are non-microscopists among you, it means that you converge your beam onto a tiny spot as small as you can, and the diffraction pattern you get is from that spot only. On the specimen, you converge your beam on the specimen. So if there are tiny little twins there, then I should hit one, hopefully, and there will be a periodic diffraction pattern and problem solved. No. It didn't work. So if there were twins there, then they should have been much smaller than 400 angstroms or 40 nanometers, which was the size of the beam. So here's the first view. This is the picture that I saw. And as you can see, there are several of the grains, or several of the crystals, are very, very black. Others are transparent, but some are very, very black. Do we have a, oh, we have a spear here. Oh, wow, wonderful. So, for instance, this one here is pitch black, and there are ones there. And so these are, so that's very interesting. So, then I took the diffraction pattern. A laser. Wow. Thank you. But by now the picture is gone. Okay, so thank you, Professor Rao. So this was the diffraction pattern. This is it. It's a perfect diffraction pattern. It's wonderful. There's no mistake. These are the points. And so when you sit at the electron microscope in the dark, it's pitch dark, and you just look there at the screen. You cannot touch the screen because there's a glass there, but I started to say, this looks very interesting. Let me count the point. And so I started to count the points around it and say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, no, cannot be. 1, 2, 3, 4, 5, 6, 7. This is exactly what happened. First in this direction, then in this direction. And I write tenfold. So this is an electron diffraction pattern from the icosahedral phase, as I named it later on, that had 5-fold rotation axis, and it is not periodic. You see, you remember the diffraction pattern that I saw a few minutes ago? There was periodicity there. If you look here, if you take the distance from this point to this point, and you multiply it by any integer, say 2, you arrive here. And there is no spot here. Instead, the ratios of distances were irrational numbers, which of course you cannot measure, because if you can measure, you don't get an irrational number, as you all know. And so the ratio of the distances between the central spot and other spot is a Fibonacci number. We will meet Mr. Fibonacci later on. Fibonacci number is T or tau, known also as the golden mean. So, and the ratio is about 1.618. So if you take this distance from here to here and divide it by the distance from here to here, this is what you get, an irrational number. But the 5-fold rotation symmetry was not the only symmetry, of course. What you do in the electron microscope, you take your crystal, and here is an sample of a crystal, and you take a diffraction from this orientation, you rotate it, you take it from this orientation, and this orientation, and so on. And so these are the series of diffraction patterns that I took. And what we have here is, this is the 5-fold that you have seen before, and then 2-fold and 5-fold here. And then in another direction, 5, 3, 5, 3, 2, and 3 again. Now, twofold and threefold are allowed in periodic material. Fivefold is not. But there was no periodicity. You see, the distances obey the same rule as before with irrational numbers. When I was a student for my master's degree, I took a class in crystallography, and when I took the exam, one of the questions was that I had to solve, prove that fivefold rotation symmetry cannot exist in crystals. And I have proved it. Had I not, I wouldn't be here. So let me show you one proof of that. Well, let's do the following. Let's take two atoms in a crystal, P and Q, and choose those that are closest together. Two atoms in which the distance between them is the minimum for that crystal. Okay, so we take these, and R will be the distance, the minimum distance between these two atoms. Now, if fivefold rotation symmetry do exist, or does exist in the crystal, then we should be able to rotate Q around P 5 times and P around Q 5 times, and let's see what happens when you do that. So let us rotate Q around P. 1, 2, 3, 4, and 5. And now there should be an atom here named Q prime. Let's do P around Q. So we have P, 1, 2, 3, 4, and 5, and Q, and P prime is here. Because of geometrical reasons, this distance is shorter than this distance, which cannot be because we chose the smallest distance between two atoms. So this is a proof, one of several, that fivefold rotation symmetry cannot exist in crystal. However, pseudo-fivefold can exist, as I told you before, if we have a twin crystal. Here is a crystal. This is a picture that I took many years before the discovery. I never published it because it was so simple, so, you know, just one of those. And so this is a crystal of from the aluminum iron system. And you don't have to rapidly solidify. You cast aluminum iron, and you have many of these. It's very common. It's twinned. So let me show you. You see, this here is a single crystal. This here is also a single crystal. In between them, you have a boundary. But not just any boundary. It's a special boundary. It's a twin boundary. And it is a twin. It's called twin boundary because look at my hands. If, for instance, you have rows of atoms or planes of atoms going this way, and in another crystal they meet this way, then you see that this is a special boundary. They look like mirror image of each other, like twins. This is why we call them twins. And in between them, we have a twin boundary. So this is the crystal. Let's look at the diffraction pattern. This is the diffraction pattern that I took from that crystal. And if you look at it, it has a 10-fold rotation symmetry, right? But no, this is because I have just taken a diffraction pattern from all of these crystals all together. So it's a superimposed diffraction pattern of 10 of these crystals. And if you want to see just one of them, here is one of them. It's one. And then you can rotate it 72 degrees, and you'll find more and more and more, and so on. Okay. Here is something interesting that I want to show you, which I never told anybody before. You see, some of the points are really little lines, like this one here, and this one here, and this one here. And the reason that we have these lines is the following. You see, this crystal and the opposite crystal have exactly the same orientation. Not exactly. There's a tiny little shift. And so you have the 2 points which are that form a little line. This is the reason why you have that. Okay. So now you see a pseudo fivefold rotation symmetry. And the pattern is similar to what I saw before. And this is why I thought that these were twins. Okay, good enough. Here is another example. These are fivefold twins in diamond, which I took years later. But this is not really an exact five-fold because you have two kinds of boundaries here. I will not go into the sigma notation now, but we have really, for those of you who understand this language, 4 sigma 3 boundaries and 1 sigma 81 boundaries. And these have been studied in detail by me in later years. But here is another five-fold. And if you take a diffraction from all 5 of them, you'll get something very similar to what I've shown you. Okay. When I set the electron microscope and tried to find the twins, I performed, as I have told you, a dark field experiment. Let me show you the result of those dark field images, and let me say about a couple of words about dark field experiments. You see, this is the diffraction pattern, and usually when you take an image, these are images, this is up there, and all these are images, and this is a diffraction pattern. So usually when you take an image in an electron microscope, you use just one point, and you block all the rest. How do you do that? You have all these points that are traveling there in the microscope. You put an aperture, and you allow only one point to go through the aperture. And you can tilt the beam so that the central point will go, or let's say that these are 2 points. Central point, whoops, diffracted point. You can do that easily in the microscope. So these are dark field images. That means that not the central point goes through the aperture, but a diffracted spot goes through the aperture. And when I was looking for these twins, I took these dark field images. Here is one. I don't know whether you see my laser beam. It's easy for me to see because I know where I aim. You don't know where I aim. So, but I hope you see that. Here is the beam. Ooh, right there. So this picture was taken from here. This one was taken from here, and this from here, and so on. This series of dark field images, and I couldn't see the twins there, as you have seen in previous pictures of 5 twins. And so there were no twins that were seen here. And what about microdiffraction? This is an experiment in which I converge the beam onto the specimen and take a diffraction pattern from a very small area of the specimen, 40 nanometers at a time. Nowadays you can converge it more. So here is a diffraction pattern. This is called microdiffraction or convergent beam microdiffraction, or seabed in short. And when I move the specimen under the converged beam, anywhere I move the specimen, I saw the same diffraction pattern. There were no twins there. Obviously, there were no twins. So at the end of that day, I knew what I don't have. I don't have a twin crystal. I have something else. Why am I saying that? Because the opponents, 12 years later, still insisted that these are twin crystals, something I knew. In day 1, which was April 8, 1982, the twins are not there. Okay. Now, let's talk about the atomic arrangement in the icosahedral phase. This picture I did not take. This was taken by friends of mine in France. This is a lattice image of the icosahedral phase. You can see the atoms here. And what you see here is a scratch in the plate. My fault. So this is the image. Okay, big deal. This is the diffraction pattern. The reciprocal space. Diffraction pattern is a cut through the reciprocal space. Almost planar cut, not quite. So what you have here is that this thing here, this image, is a Fourier transform of the diffraction pattern. Okay, lovely. What you can do with it, though, you can take this picture, this image, put it on a slide, make it very small, and shine a laser beam. Laser beam, here, laser beam, you shine through that specimen. I wish I had it. I could show you the diffraction pattern on the wall. It's very easy to show. So this is an optical diffraction, which looks the same. It has the same symmetry. So you say, okay, big deal. This is one Fourier transform, another one, and this should be equal to this. Okay, so what about it? What you could do in the electron microscope is choose the area from which you take the diffraction pattern. So let's say that you choose this area, and let's say that you receive this image. And now you can shrink that area. You can close the aperture. Here goes. And as you close the aperture, make it smaller and smaller, this diffraction pattern does not change. It will disappear for lack of information, but it doesn't change. This was the final proof, really, that, hey, no twins. Besides, you don't see any twins. But when I say that I don't see any twins, this is not scientific. Somebody else will say, okay, you don't see, so what? But the experiment I just showed you is science. This is just for fun, a more modern picture of the icosahedral phase, and you can see all those. This is real space. These are atoms, actually. You can see all those tenfold wheels there in each and every corner. Okay, that was everything. Was 1982. In the first, what I described to you up to now was one day. It's going to be a long talk. One day. And then I repeated these experiments just to find out if I did make any mistake. I didn't. I always got the same results. And I found the range of composition in which the phase existed, and so I will not bother you with all this. And then I came back to the Technion from my sabbatical. And during my stay, the reactions to my findings were not so nice, as I will describe shortly. But the first person who really volunteered to help and join force was Ilan Blech, at the time professor at the Technion. He did two things. He helped elucidating the structure and proposed a model, later on called icosahedral glass model, in which icosahedra in space join arbitrarily, like in glass, but maintain their orientation. And he created a computer model, and indeed the reciprocal space of that model, and found out that the diffractions in the model and in my experiment fit. And so we sent a paper for publication. This was in the summer, in September of 1984. We sent it to Journal of Applied Physics, and something marvelous happened. They rejected it right away. Whoops, came back. So I took that, and they recommended that I send it to a journal of metallurgists, because the community of physicists will not be interested in this paper. I said, well, all right. So I sent it to Metallurgical Transactions, and in this department, many people, of course, recognize metallurgical transactions, and they accepted it. But they published it months and months later, deep into 1985. In the meantime, here's the story, but we'll skip that. In the meantime, I sent the paper. I have to remind you, those days, we sent papers on paper, envelope, stamps, and it took some time to arrive. And so I sent it, and then I showed the paper to my host at NBS, John Kahn, an eminent scientist. And we had some arguments and so on, and finally he said, oh, Danny, we have something fantastic here. And he proposed to write a different paper based on this paper, only much shorter, without the Ilan Blech model. And we have sent it to Physical Review Letters. He added also another person to the paper, Denis Gratias, who is an eminent mathematical crystallographer from France, who came to NBS. The three of us sat down, wrote the short paper, and sent it to Phys Rev Letters, and it was published very quickly. Ilan Blech is included here too. And then hell broke loose, because then we opened the field, and many scientists around the world joined us immediately, because in my paper I described how I prepared the specimen. So anybody who had some facility could make the specimen, stick them into the microscope, and I started to get phone calls from the world. Hey, Danny, we have it, we have it, we have it, wonderful. And from there on, the field started to expand, not like a big bang, but like a small bang. Huh? There are also Nobel laureates in physics, you know. Okay, so this was the paper, and it was published in November 12, 1984, and opened the field. Now, let me dedicate some time to icosahedral symmetry so that you know what I'm talking about. This is an icosahedron. By the way, this particular icosahedron is made of wood, fine work by a friend of mine. And the symmetries that you have here, it has 6 5-fold axes. What does it mean, 5-fold axes? If you look from this point down here, from this point to the center of the icosahedron, you'll see a 5-fold rotational symmetry. You can rotate it 5 times and it will repeat itself. And it has 10 3-fold axes. 3-fold axis is exactly what you see here. This is a 3-fold axis. Yeah, oh, wow, wow. Thank you, Professor Rao. Oh, you're such a help. So this is the 3-fold. This is the 5-fold. Okay. And 2-fold is here. 1, 2. Perfect. Thank you so much. Much better. Okay. So this is icosahedron. And of course, anybody who plays football can see the icosahedral symmetry in the football. This is European football, not American football, of course. We have some Americans here, so it's different. And so this is a 5-fold, 3-fold, and 2-fold. Okay. Now, between 1982 and 1987, these were the years of rejection, and the rejection was divided into 2 parts. In the beginning, when I was alone in the laboratory, starting to talk to people about these crazy diffraction patterns, I received mixed reactions. My host, John Kahn, came to me and said, Danny, this material is telling us something, and I challenge you to find out what it tells us. This was the positive reaction. Negative reaction was from my group leader, who came to my office one day, smiling sheepishly, putting a book on my desk and say, Danny, please read this book, and so that you will understand that what you are talking cannot be. And I said, you know, I know this book. I don't need to read it. I'm telling you, this is different. And then he went and came back. I don't remember when, a few days later, and he said, Danny, I need you to leave my group. You are a disgrace to my group. I don't want to hear. So I left my group. And that didn't mean much. I just practically meant that I reported to another secretary. I didn't move from my office or anything. Nothing happened really. But it gives you this spirit between encouragement to total rejection. But nobody offered to help. The first one that offered was Ilan Blech. And this is how I felt during that period, the first period of time. Let's go back. This was from 92 to 82 to 84. And when we published, I was not alone anymore, but the International Union of Crystallography did not accept these results because it was the International Union of X-ray crystallography, and we did not have single crystal diffraction pattern from any quasi-periodic material. Why so? Because they were very small as 2 microns. And you cannot take an X-ray diffraction pattern from a single crystal that is 2 micron. You have to hold it somehow. It took 3 years, from 1984 to 1997, for a couple of groups in the world to grow large enough crystals. One group in France, another group in Japan. They grew large enough crystals. They took X-ray diffraction, and in 1987, they sent me these diffraction patterns, and I presented these patterns in the meeting of the International Union of Crystallographers in Perth, Australia. And these were, oops, no, I'll show you the patterns later. I'm sorry, it's not ordered. Okay. So the rejection by most of the community stopped at that time, but not everybody agreed, and we'll go to that later on. Here is an anecdote. This is, the month is July of 1986. July of 1986. This line describes to you 1 over n, when n is the number of pages in the publications on quasicrystals. Okay? 1 over n. And so we connected the line and extrapolated that by December of 1986, the number of pages in the publication on quasicrystals will reach infinity. So that all the trees of the Amazon will have to be cut just to process the paper to publish all these publications. So we worried. But that didn't happen, as you know, and if you go to the Amazon, there is a proof. But this was the feeling, that there's an explosion of good, excellent scientific work around the world. The last person to reject quasi-periodicity was Linus Pauling. Linus Pauling, here he is in his last years, and from him came the main objection to quasi-periodic nature of quasicrystals. And here is his some good words about him. He was really an eminent scientist, possibly the greatest chemist of the 20th century, if not one of the greatest. And he got Nobel Prize in chemistry. He did. But also in peace. 2 Nobel Prizes. And he was a flamboyant speaker. He stood on stages almost like a politician, waving hands, and he had a crowd of followers, which was the American Chemical Society, a huge society with very, very many thousands of members. And whatever Linus Pauling said was, of course, correct for them. But in this case, and in several other cases, he made a mistake. So during the last decades of his life, he died in 1994, he fought quasi-periodicity. And he did that by proposing a larger and larger models of periodic structure that when would twin, they will show the same diffraction pattern that I had. And any time he managed to publish, many of his publications were rejected, especially if I was the reviewer. But when he managed to publish something, there was already immediately almost somebody in India or China or somebody said, no, Professor Pauling, you're wrong, your analysis is wrong, and here is a paper that shows that. Died and said, oh, well, that was an approximate, but now we'll have a larger and larger. Yes, quasicrystals are, you can say that are an infinite periodic crystals, infinite size. Okay, well, all right, so we meet in infinity. Okay, let me now take you to a little bit more deeper understanding of quasi-periodicity. Okay. Let's say that we have, this is called the cut and project method, and it was introduced to me in 1985 by 2 French scientists, Katz and Dunant, in an international school for mathematics that was organized by Louis Michel, an eminent French mathematician. And they showed the following. They said, okay, let's take a periodic lattice and make a cut in it. We will cut a strip in this periodic lattice. But we will cut the strip in a particular direction so that the angle alpha is an irrational, the tangent is an irrational number. Now think about it. If the tangent is an irrational number, that means that this line will never meet any lattice point, ever. Because if it does, then the tangent is this divided by this, which is a rational number. But this is an irrational direction. And now that you made this cut, you can take all the lattice points within this strip and project them onto this line. And when you do that, you get a series of distances. This is one distance, another. And if you look well, you see that there is a long, long, short, long, long, short, long, short, long, long, short, and so on and so forth. And this fits exactly the Fibonacci series. Okay, this is a projection of a 2-dimensional space on a 1-dimensional space. You can do the same thing with 6-dimensional space, Do it at home. You can try it at home. 6-dimensional space, project it onto a 3-dimensional space. If you take a periodic 6-dimensional space, cut and project onto a 3-dimensional space, you will get quasi-periodic arrangements in 3 dimensions. You'll be surprised when you do it at home. Okay, let's repeat what I just did. And here are the 2 lines with the angle alpha, which is the Fibonacci, the tangent is Fibonacci number. Now, let's take 2 lines which are almost close to those lines, but these are periodic, and the angle is 11 divided by 7. What does it mean? Well, I take this point here and count 11 divided by 7, and this is the tangent of this angle. And these are close together. But the red line is periodic, and the black line is not periodic. And because they are close together, then crystals which obey those large unit cells that are approximately quasi-periodic materials, we call them approximants. So see what happens. While as before, quasi-periodic materials were outcasts, now we have materials which are special because they are almost quasi-periodic. They are approximants. So now we have a new class with periodic materials which are approximants. Okay, so this is the diffraction patterns that they sent me. This is the example from Anpeng Tsai from Japan, from Tohoku University, but I also have the French pattern. These are beautiful patterns. I present them in 1987 in Perth, Australia, and the community decided to redefine crystals, which was possibly the major achievement and the basic acknowledgement that quasi-periodic materials are indeed included in the family of crystals. Now, let's say a few words about Leonardo Fibonacci of Pisa, because he was such an important person at the time. And this is his picture. Look at his eyes. I mean, he's so tame. He's wonderful. And this is a statue that is in his graveyard, and it is behind the inclined tower of Pisa, under a roof. It's a very interesting place. So what Fibonacci did in 12,002 is to propose the Fibonacci rabbits, and here is the story. Let's say that the male rabbits are not necessary, female reproduce by themselves. Great. And here is the female rabbit, and in the first month we have 1 rabbit. In the second month, she gives birth to a little one, so we have 2. In the third month, this grown-up gives birth to another little one, and this one grows up. It cannot reproduce in the first month. It has to grow up. And this rule continues. So this one gives birth to a little one, this little one grows, and this big one gives birth to another one. So we just follow the rules. That's it. And now what you can do several things with these numbers. And the numbers on the left are just the number of rabbits that exists in each and every month. So in the first month there is 1, then 2, 3, 5, 8, 13, 24. Now let's look at this number. 21, the last number, is 8 plus 13. So this is rule number 1. Okay? So that an, the number of rabbits in any n number, equals the number of rabbits in the previous month and 2 previous months, 2 months previous to that. Also, if you take the limit of this ratio, which means this number divided by this number, but in infinity, an divided by n minus 1, you get this number 1 plus 8 root 5 divided by 2, which is the Fibonacci number, irrational number, and everybody is happy. Okay. So this was published in his 1202 book. This is quasi-periodicity in 1 dimension. Let's go to 2 dimension. Penrose styles. Roger Penrose is with us, and he is a great British mathematician, And years ago, he designed these two tiles which pave a plane quasi-periodically by only two rhombi. A fat rhombus, here is the fat rhombus, and here is the thin rhombus, up here, fat and thin. And that's all we have here. The colors are just for fun. So this was very interesting, and Gardner published it as mathematical games in Scientific American, and he actually made these tiles famous. There's another mathematician named Alan Mackay, also British, who took Penrose tiles and looked at the reciprocal space of these Penrose tiles. That means that he took this on a slide, and with a laser beam he showed that when you do that, you get a nice five-fold diffraction pattern. Lo and behold, he did it in 1981, and that matched exactly my findings from 1982, published in 1984. Problem is, I didn't know about that. I knew about Penrose tiles, but I didn't know about Mackay experiment. People who did know were Paul Steinhardt and Dov Levine. Paul Steinhardt was the thesis advisor of Dov Levine, and they made the connection between Penrose, Mackay, Schechtman, Blech, Kahn, and Gratias, and say, this is this. So they proposed the mathematical quasi-periodic model to the community. Their paper was published just a month or so, a month or two after our publication, and it created the mathematical model for quasi-periodicity. They also coined the term quasicrystals, which I don't like because they are not quasicrystals, these are crystals. But these are certainly quasi-periodic, as they have suggested. This was 2 dimensions. 3 dimensions, here is a crystal. This is a quasi-periodic crystal taken in my laboratory. We grow them in abundance, and this is a little one. You see, this is about a couple of microns, maybe 4 microns inside. You could not take an X-ray diffraction pattern from such a crystal, but you can see the 5-fold rotation symmetries here quite clearly. Okay, now this is just for fun. This was taken by Anpeng Tsai, my friend from Tohoku. Look at those beautiful crystals. The color are artificial. This is just a decoration, the color. But you can clearly see the 5-fold rotation symmetry and the 3-fold and so on. Okay, while as before, order was synonym to periodicity, I think that by now the community and you are convinced that order can be periodic, it can be quasi-periodic. And this is a paradigm shift in the science of crystallography. And it was a brave move on the part of the International Crystallographic Union to adopt the new definition of a crystal. Now, before I finish, I would like to ask myself a question that you may not dare to ask later on, so I answer it first. Why quasi-periodic materials were never discovered before 1982? Now, bear in mind that between 1912 and 1982, hundreds of thousands of crystals were investigated thoroughly by excellent scientists with high precision. How come nobody of those hundreds of thousands of studies saw quasi-periodic materials? Well, is it because they're very rare? We'll answer that. Are they not stable? You look at them, they disintegrate. Or you touch them, they disintegrate. Maybe. Are they difficult to make? Only Daniel Schechtman in his secret lab managed to make them. Maybe. So let's answer that. Are they rare? Oh no, they're not rare. Not rare at all. What you see here is a partial list of the quasi-periodic materials that exist based on aluminum alone. And there are other elements, as you know very well. So there are hundreds and hundreds of them. No, this was not the reason. There are very many quasi-periodic materials. Are they not stable? Many are not stable, but what does it mean not stable? When you rapidly solidify them, you create metastable phases sometimes. That means that when you heat them up to 300, 350 degrees C, they will transform. But at room temperature, very stable, no problem. That's not an answer. Here are some quasi-periodic crystals which are stable, and there are more. They melt congruently. Okay, maybe they are very difficult to make. Not at all. They are very easy to make. Quasi-periodic material can be made by many manufacturing technologies. You can cast them, you can rapidly solidify them, you can single crystal grow, you can do them by electrodeposition, by CVD, PVD. Any way you prepare any other material, you prepare quasi-periodic material. Very easy to make. Maybe there are rare elements, praseodymium mixed with gadolinium. No, no, no. We talk aluminum, we talk iron, copper. Oh, abundant, cheap, no problem. So why? Well, let me give you my answer. Answer number one, TEM. Quasicrystals had to be discovered by transmission electron microscopy. This is because they were very small. And for the transmission electron microscope, any small crystal is a single crystal. There's no too small crystal for an electron microscope. Not X-ray. So, okay, you want to discover quasicrystal? You should be an electron microscopist. Thank you very much, I am. Professionalism. It means that you have to know what you're doing. Getting a driver's license on a transmission microscope doesn't mean that you know what you're doing. It only means that you know how not to destroy the microscope. And then they let you work on it. But that doesn't mean that you know what to do with it. So you have to be a professional. Okay? And you have to know the capabilities, and you have to know your crystallography, and you have to know what's allowed, what's not allowed, and so on and so forth. You have to be a professional. And then you have to have tenacity. That means that if you discover something and you bite, stick to it. Just don't let go until you understand what's going on. Be open to criticism. Listen to other people. But if you are convinced, as a professional, remember professionalism? If you are convinced that you are right, stand tall. Fight for your discovery. And if somebody comes with evidence which are convincing that you are wrong, which happens many times, then say, okay, sorry, I'll try again doing something else. But if nobody comes with such evidence, don't let go. And you have to believe in yourself. What does it mean you have to believe in yourself? It means, and I'm talking to the student if you didn't pay attention, so pay attention. You have to be a professional in something in order to believe in your science. And it is never too late to become a professional in anything. It doesn't have to be electron microscopy. It can be anything, but become a professional. And as students, try to learn anything about the field that interests you. And talk to your professors. Ask them questions. Bug them. They will answer you. Yeah. Professors are very interested in interested students. They really would like to talk to you. So find an area, become a specialist. Finally, you have to have courage. I was early in my academic career. Linus Pauling was late in his academic career, and we were like this. In public, Linus Pauling was used to say, there are no quasi-crystals, there are only quasi-scientists. And, but, so sometimes you have to say, okay, I believe in what I have found, and that's that. By that time, I had so many supporters. Linus Pauling died in 1994, a non-believer. Let me tell you my last story. I met with him several times. Always we were very friendly and polite to each other, and we agreed on everything, vitamin C included, but not on quasi-periodicity. A couple of years before he died, he wrote me a letter that arrived in the mail. Remember, mailman? Saying, hey, Danny, let's write the Schechtman-Pauling paper together on quasi-periodic materials. And you will be first, he said. I answered with a letter. Professor Pauling, I will be delighted to publish this paper with you, but let's first agree that quasi-periodic materials do exist. So he wrote me a letter back saying, well, that may be too early for that. That was the end of our communication. Thank you so much.